We present selective visual representations improve convergence and generalization for embodied AI. Human vision doesn't process every single detail in the scene. We selectively filter out details and focus on the most relevant parts depending on the task at hand. When searching for the remote control in our living room, we overlook many visual details in the scene. We focus on flat surfaces such as coffee tables or TV stands where the remote is typically placed. Similarly, when looking for a book, our attention is directed solely to the bookshelf, disregarding other visual stimuli. In cognitive psychology, selective attention is a mechanism where perception is filtered based on the internal goals. In the famous gorilla experiment, individuals are asked to count the ball passes between white shirt players and fail to notice a black gorilla crossing the scene. Embodied AI agents have similar goal-directed behavior, such as navigating to a specific goal or relocating target objects. However, they employ off-the-shelf visual backbones. These encoders are pre-trained on general-purpose vision tasks and stay frozen throughout the embodied training. Consider an agent tasked with locating a key in an environment. Pre-trained vision encoders like Clip or Dino capture an abundance of task-irrelevant details, such as distracting objects, their colors, and attributes. These details introduce noise in the learning process and distract the agent from more important visual cues. A goal-driven visual encoder based on selective attention will only retain the most relevant information to the task, such as identifying flat surfaces likely to hold the key. Standard embodied AI architectures contain 3 encoders to embed the visual observation, goal, and previous action. The 3 embeddings are fused to form a goal-conditioned visual representation, often with dimensions as large as 1500. A recurrent neural network followed by a small actor could decide an action based on the observations in the past. We propose a compact codebook module as a goal-conditioned bottleneck to capture task-related information. This allows the policy to focus solely on decision-making based on the filtered observation. The codebook contains a small set of low-dimensional latent codes jointly optimized for task reward. The compressed visual embedding is a convex combination of these low-dimensional latent codes. Similar to our codebook bottleneck, previous bottleneck architectures have been applied in computer vision, natural language processing, as well as reinforcement learning and robotics. Next, we go to the various benefits of the codebook bottleneck representations. We outperform state-of-the-art across 5 embodied AI benchmarks. Our agent achieves higher success rate and lower episode length, travels in smoother trajectories, and is more efficient in solving the tasks. We observe noticeable improvements in agent behavior, namely exploring more efficiently and traveling in smoother trajectories. While the baseline agent takes redundant rotations and performs poorly in exploration. Comparing the first-person views of the 2 agents reveal that the baseline agent frequently makes redundant rotations, whereas our agent follows much smoother paths. To investigate the transfer to a new visual domain such as a new simulator, we keep the decision-making modules frozen and only fine-tune the parameters responsible for extracting visual cues. Our architecture shows better transfer when faced with similar tasks in new visual domains, as shown by the huge improvement across all metrics in the new simulator. We employ linear probing for a set of primitive tasks to evaluate the information captured in our embeddings. While the new representation is suboptimal in object detection from non-goal categories, it's more effective in predicting task-related information such as goal visibility and proximity. GradCam attention maps further show our model effectively ignores distractions and only focuses on object goals. According to the nearest neighbors, our visual embeddings group frames by goal visibility and proximity, while the baseline focuses on scene semantics. In this example, our nearest neighbors display frames where the object goal is clearly visible, similar to the query image, while the baseline neighbors consistently display a wooden table. Here the goal is seen at a further distance in all our nearest neighbors. When the goal is not visible in the query frame, our nearest neighbors are based on overall scene layout, whereas the baseline neighbors are selected based on appearance and texture. By replacing the clip encoder with Dino v2 pre-trained encoder, we confirm that the codebook is not dependent on any specific visual representation and can adapt to different visual backbones. For code and pre-trained models and more qualitative examples, please check out our website.